In this example, we will graph the set of parametric equations by making a table of values. This graph will map what I call the flight of a paper airplane, and I recommend to use increments of pi over 2 to go to at least t equals 3 pi. The equations we'll be working with is x is equal to t minus 3 times sine of t, and y is equal to 4 minus 3 times cosine of t. We do have a restriction that t has to be greater than or equal to pi, but what that means is that we are going to have a starting point of wherever time of pi is, and then we are going to continue infinitely along the trace that we have found. Let's see what this will look like. For this one, we are going to do quite a bit of rounding, so I'm going to keep my calculator up on the screen for a while for this one. So, for our set of values. As per the restriction on t has to start at minimum pi, so that's where I'll begin. And from my hint, it said to go from increments of pi over 2. So let's go ahead and do that. So that'd be pi, 3 pi over 2 would be next, 2 pi, 5 pi over 2, and then 3 pi. So it says to go to at least 3 pi. If we need to do more points, we can. But we'll use those in order to estimate values of x and y. Starting with pi, x is going to equal pi minus 3 times sine of pi, and sine of pi is 0, so that's just going to give us pi, or 3.14. It may seem weird that x is defined as a function using sine, but we've just in the past conventionally assigned sine and cosine to y and x respectively. And talking about parametric, you're free to really do anything. With y next, we have 4 minus 3 cosine of that, so 4 minus 3 cosine of pi, which we should know is negative 1. So that'll be 4 plus 3, or 7. Then with 3 pi over 2, I'm going to get 3 pi divided by 2 minus 3 times sine of 3 pi over 2, which is negative 1. So that's really just going to be 3 pi over 2 plus 3, so 7.71. And then 4 minus 3 cosine of 3 pi over 2. Cosine of 3 pi over 2 is just 0. So that's just going to give us 4. Next, with 2 pi, you can start to see where some of this pattern is going, particularly for the values that we do know. If I do plug in 2 pi in for x, I'm just going to get 2 pi minus 3 times 0. Sine of 2 pi is 0. So I'm really just going to get 2 pi for the next value, which is 6.28. And then if I plug in 2 pi into the second equation, they'll give me 4 minus 3 times 1, or just 1. With the next value after that, 5 pi over 2, for the x value, I'll have 5 pi over 2 minus 3 times sine of 5 pi over 2. Sine of 5 pi over 2 is just 1, so that's just going to be 5 pi over 2 minus 3, but we could show that. Minus 3 sine of 5 pi over 2. So that's just 5 pi over 2 minus 3, which is apparently 4.85. And then if I plug in 5 pi over 2 in for the y equation, cosine of 5 pi over 2 will equal 0. So this is just going to be 4 minus 0, or 4 again. You may notice a pattern with the values in y right now. With 3 pi, which is the last point to have as a recommendation, and hopefully we can figure out what's happening from there. With 3 pi in for x, I'm going to have 3 pi minus 3 times sine of 3 pi, the latter of which is 0. So that'll overall just give me 3 pi, which is 9.42. And then if I do that for the y equation, cosine of 3 pi is -1. That's 4 minus 3 times -1, or 4 plus 3. We're going to get 7 from that. Now this should probably be good. I'll test one more point just to make sure. I'll do 7 pi over 2 as well. Why not? For the first one, for x, that'll be 7 pi over 2 minus 3 times sine of 7 pi over 2. Well, sine of 7 pi over 2 will give you -1. So this is really just going to be 7 pi over 2 plus 3. But again, we can punch all that in just to make sure. We'll get 13.995, or I'll just say 14. And then if I do that for the y equation, cosine of 7 pi over 2 will be 0. So this is overall just going to be 4 minus 0. That should probably be good. Let's plot this now. My first point I plot in my time order is x of 3.14, y of 7. So 3.14 up to 7 would be starting up at the top here. That's my first point. My second point is 7.71 and 4. So 7.71 is closer to 8, and it goes up to 4. Just about here. That's my second point. My third point is 6.28 and 1. So that means we've actually traveled back to the left and only go up a distance of 1. So that's our third point here. Our fourth point has the same height as the second one, but it's at 4.85. So it seems like we're still traveling to the left here. So that about should be the fourth point. Same height as the second. And then we have 9.42 and 7. So it seems like we're now going back to the right. So 9.42 and 7 would put us about here for our fifth point. And lastly, the last one I did was 14 and 4. Well, 14 is a bit off of our track here, so 12, 13, 14 would be maybe over here, and 4. So that'll put us here for our sixth point. If I go through these, and you can test more points in between if you would like to get more of an idea, but this is going to curve smoothly from 1 down to 2 and back, up towards 4, and then up towards 5, and back down again towards 6. If I draw arrows in between my points, I can show the track that this is following. And because t is not restricted to have any high-end value, this is going to continue doing this pattern over and over and over again infinitely. So this is what we mean by the flight of a paper airplane. When you throw it, it very often will dip down and will start to do some loops. No, it will not do infinite loops, but it's, I guess, assuming that there are less forces than usual. But that would be this parametric set of equations.